All right, so what we're going to do in this video is finish up note set 12 and also finish the homework that was associated with homework 12. So pull those out, and we finished the front side where we went over what London dispersion forces were and also dipole forces. And on the back side for you guys, note set 12, intermolecular forces, and we've got hydrogen forces to talk about and also ion dipole. So crunchy noises, let me get zoomed in. So this is the back side of note set 12. So recap, I know it might be excessive, but this is a really hard chapter. So recap, IMFs happen between different molecules when you've got a partial positive on one side attracted to a partial negative on the other. And there's 4 different kinds. We already talked about London dispersion forces, which are the weakest. I should have just written LDF. Oh well. All right, London dispersion forces, which are the weakest kind. Then we talked about dipole interactions. And then hydrogen comes next right here, but you see hydrogen is actually a subcategory of dipole. So I just don't want you to get confused because there's London dispersion, dipole, hydrogen is a subcategory of dipole, and then the other one will be ion dipole, which I guess you could say is also a subcategory of dipole, but it's pretty unique, so I would leave it in its own category. Important thing is that hydrogen goes underneath the dipole. Hydrogen is a glorified special, like the fan favorite of dipole. So some textbooks will call this type hydrogen bonding. I don't like to call it hydrogen bonding because it's not actual bonding. Bonding is like when my arm is bonded to me and it won't rip off easily. Forces are just connections. Hydrogen forces is what we're talking about, but people say bonds, hydrogen bonding, and textbooks say it, and it gets really confusing. So I'm going to try and avoid it. But that's why I have it written and crossed out. It is the glorified strongest form of dipole-dipole interactions. Basically, it is dipole. It only happens with polar molecules that already have a permanent partial charge and a permanent partial negative charge. What makes it special, though, is when, let's see, how do I write this? What makes this type special is when the partial positive is specifically a hydrogen, and the partial negative is specifically nitrogen or oxygen or fluorine. It's the same thing as dipole because you have a polar molecule with a partial positive, partial negative. But the H is going to be here and FON is on the partial negative. It reminds me of that SpongeBob song. F is for friends who do stuff together. I guess it's fun. U is for you and me. N is for anywhere, anytime at all, down here in the deep blue sea. And then Plankton's all like, F is for fire that burns down the whole town. U is for uranium bombs. like N is for no survivors or something. So anyway, that's what I always think of. I always think hydrogen bonding, which again, bonding, not a real word, but hydrogen forces are really fun. Or if you go this way, you could say you've had enough of this. So there you go. There's some tricks for remembering. So here is a cutout of the periodic table. And what this is showing, the numbers underneath are showing the electronegativity values. Electronegativity goes from 0 to 4. 4 is the most electronegative. 0 would be the least. The more electronegative you are, the more you pull on the electrons. So notice that fluorine is the most electronegative element. He's pulling max at 4. Oxygen is 3. Nitrogen is 3. These are like the heavyweight mega polars. When those 3, either one of them is the partial negative, and when the hydrogen over here is the partial positive, that's when we get a hydrogen bond, aka hydrogen force. IMFs between hydrogen bonded to nitrogen, oxygen, or fluorine on one molecule, and either nitrogen, oxygen, or fluorine on an atom of another molecule. Great. Since NO and F are super electronegative, it makes the partial positive even higher than normal on the hydrogen. Okay. This higher than normal partial positive charge is attracted to the negative end of a dipole formed by a different molecule. Okay, so it's just a stronger form of dipole. So here are some water molecules. Water, of course, H2O, oxygen, oxygen, oxygen. He's one of the heavyweights. So I'm looking, if that's an oxygen, that's a hydrogen. The oxygen from one molecule is interacting with a hydrogen on the other. Okay. I'm going to relabel this. So oxygen, hydrogen, oxygen. That's exactly what we're looking for. We're kind of looking for a hydrogen sandwich. On one side, it's got to be bonded to NO and F. And sorry, on one side, it has to be bonded to NO or F. And on the other side, it has to have an attraction to NO or F, which is exactly what we have. Okay, crunchy noises, I'm zooming in. So here in this picture, we have methanol and water, CH3OH and H2O. This is the oxygen, hydrogen, oxygen, hydrogen, hydrogen. We're looking for that hydrogen sandwich. On one side, it's bonded to FO or N, and on the other side, there's an interaction. If that's the case, then we call it DIMF hydrogen. Ooh, check this one out. This is kind of cool. So let me get a different shade. This is 2 molecules. So this is like, this is molecule 1. That's molecule 1, and let's do like really light blue so we can still see it. Here's molecule 2. And we're wondering what kind of intermolecular forces are happening between them. Hydrogen sandwich. On the one side, it interacts with FON. On the other side, it's bonded, F-O-N. That works. It also does it down here. On the one side, bonded to F-O-N. On the other side, attracted. On the one side, bonded to F-O or N. On the other side, attracted. Ooh, this one's kind of interesting though. Okay, so far it's just been lots of oxygen, hydrogen, oxygen sandwiches, right? Oxygen, hydrogen, oxygen sandwich. This is gonna be a little bit different. This still works though, because oxygen is bonded to hydrogen, and on the other side, it can have an interaction with FO or N. So it doesn't have to be the same. It's just one side bonded, one side attracted, and it needs to be FO or N. On this side, it's the oxygen. And on this side, it's the nitrogen. So that one works. The IMF is in yellow. On the one side, hydrogen is bonded. On the other side, there's an interaction. NHN, that works. Same over here on that side, but I'm not going to color it. Hydrogen forces. Hydrogen forces are important in two substances they use a lot on the AP test. The first one is that they look at DNA, and the other is water. So DNA and water. In biology class, they would be like, look at this picture. Look, this is the sugar phosphate backbone. And you'd be like, why is that or at least I would be like, why is that a circle? Why is that a not a pentagram. It's like satanic. A pentagon. I'd be like, why is that a pentagon? Why is that like these shapes are dumb. Like they look like they were made in like Microsoft Paint or something, if that. And then when I got to be like a big kid in chemistry, I started to realize like, oh, okay, so this is what it actually looks like. And this is the dumb version. Like, okay, cool. So labeling, it's saying this here is an adenine. This chunk is cytosine, guanine, thymine, and then those are the important bits. The rest of it is this backbone. Seeing it? But like with real molecules. All right, so there's the backbone. These are the bases. And check this out. In the textbook, they're always like, look, G and C have 3 interactions. Woo, memorize that. And I'm like, how am I supposed to know that these little stupid shapes have 3 interactions? But look at how cool it is. You can actually see them when you draw out the formula. Oxygen, hydrogen. Like you can see each of those is an H force. There are 3 hydrogen bonds, aka hydrogen forces, that hold together guanine and cytosine. There's only 2 that hold together adenine and thymine. So a question that you might get on the AP test is, explain why someone with more GC DNA, why would theirs be stronger than someone that has more A's and T's in their DNA? And they'd probably show you a picture and you'd say, oh, well, the GC has 3 hydrogen bonds, but I don't like that word, has 3 hydrogen forces, while this one only has 2. IMFs are what keep molecules together. So if you've got 3 of them instead of just 2 of them, you're going to be held together a lot better. So there's the emphasis on DNA. The other thing that the AP test likes to bring up is the intermolecular forces in water. They'll say like, why does it take so much energy to boil water? And you'll say, oh, because water has hydrogen forces, which are really strong. You have to overcome them. But one of the things that I think is really cool is hydrogen bonding, hydrogen forces, is what lets like animals and bugs walk on the surface of the water. So I have a video here of my toilet. And one day I went to the bathroom and I saw there's this spider. You can see there's like the bottom, like where you flush. There's a spider in the toilet bowl. And it's actually really cool because, let me zoom in. You can see from the shadow, like the little dots are where his feet are kind of bulging the water. So here's the video. So as he walks, you can see like not only here is he pushing down and it's not breaking the surface tension, but you can also see the shadow of like where his feet are, which is really cool. All right, so now there's hydrogen. It's just glorified dipole. It's when you've got that hydrogen sandwich on the one side, it's bonded to either N, O, or F. And then on the other side, it has an interaction with same ones, N, O, F. Ion dipole is the last one, and it's exactly what it sounds like. You have an ion and a polar molecule coming together. So polar molecules have those partial charges, not full charges, because if it has a full charge, then it's an ion. So ion is like full charge, 100%. Dipole, aka polar molecule, only has partial charges. So if I have an ion, a cation, a full 100% positive, positive, positive ion, the negative side of like a dipole that has partial positive and partial negative both, you see how maybe this partial negative could want to have a little attraction to that full positive over there? Or what if, new example, we had an anion that was full negative. This would like whoop, flip, so that way the partial positive end could be like, oh, shoo la la, very attracted. There. So that's what ion dipole force is. It's a full charge on an ion that attracts and has an interaction with a partial charge. So normally, let me zoom in. Normally how you're going to see this drawn is something like this. You've got an ion in the middle with a full charge. So make sure to make that nice and like obvious that this is like a full charge. This is also a full charge negative. The partial negatives are the ones that want to interact. My positive charge brings all the my full positive charge brings all the partial negatives to the yard. So there would be the ion dipoles. Now it flips for the negative, because with the negative, they're like, you put your partial positive side in. Wow, there's a lot more of these ones. Partial positive wants to be in so that it can interact. It's not as obvious in the pictures that are going on right next to it, but it's the same idea. This is the positive charge. Here's a water molecule. And then oxygen, partial negative are the ones that are coming in to touch it. And when the ion is negative, all of the partial positives coming, like the molecule. It looks like a Kirby. Dun, 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 dun. But like on this one, we've got the Kirby's head going in, and then this one's going in feet first, depending on the charge. So ion dipole, ID, ion dipole forces are the strongest ones because of that full charge on the ion. Partial positive will line up to be with the negatives. Let me zoom out, sorry. Didn't realize that wasn't on the screen. Partial positive is going to line up with the anions, which are the full negative charge. The partial negatives are going to line up with the cations, which have that full positive charge. It's usually like the easiest one to recognize because the pictures just look different. It's like one thing in the center and everything around it, preferentially orienting. All right, I lied to you. I'm sorry, I did. So this whole time I've been saying that intermolecular forces are forces that occur when different molecules are interacting, intermolecular forces. But, and that's normally the case, I'd say like 99% of the time. But what if we had a molecule that was like so big, like just really ginormous, like super, just like here's my molecule. It's like so big that this side could fold itself around and interact with this side, almost as if they were different molecules. That can still be called intermolecular forces. If the molecule is so big that it can fold backwards on itself and the two ends can interact as if they were separate, then that's like the exception to this. And that's what the bottom of the paper says. I have to teach it to you because the AP curriculum says so, but do not stress out about it so much. It's just saying that when you go to AP Bio, you're going to learn about intermolecular forces. And you might be confused because your chemistry teacher said intermolecular forces occur between separate molecules. And then your biology teacher will be like, no, no, no. If the molecule is big enough that it can fold back on itself, it still works. I mean, technically that's true, but this is just the little nuance that they want me to teach you. But for the most part, I'm still just going to highlight IMFs normally occur between separate molecules. because that's really what we're looking at. See, don't need to memorize. Don't need to memorize that. Just for AP Bio,